Hello, and welcome to a new series in videos. In this series, we will be focusing on these three main aspects. So go ahead and take a screenshot, pause this video, whatever you may need to do so that you can refer to these points throughout the next videos. With that being said, this first video, we are given a water flowing through an aqueduct with a width of W. It is inclined at an angle relative to the horizontal and is flowing at a volumetric flow rate of Q. We are given the assumption that the shear stress of the wetted wall to be equal to that for an equivalent circular pipe with the same average velocity, and to derive an expression for the height h of the water flowing along the aqueduct. Then later write a Python code using the root function that we've gone over before to solve for h when we are given w of 0.5 meter, the volumetric flow rate of a meter cubed per second, and the aqueduct is inclined 15 degrees relative to the vertical. So with that being said, let's go ahead and jump into the whiteboard. Hello, and welcome back to the whiteboard. So you can see I've gone ahead and drawn the situation that we are apprehending on the whiteboard. And what we have is an open aqueduct of a square or rectangular site with water flowing through it. It has a width of W and the water is at a height of H. And of course, this aqueduct is inclined at an angle of theta. Theta is 15 degrees, however, it is a little bit exaggerated just to get a little bit better picture of the situation at hand. So that the water flows down towards the second point and through the aqueduct. And so as I said before, we will be using derive some expressions for h and g and the different ones so that we can go ahead and plug them into a Python code and use the root function to optimize the givens so that we get an expression or a value for the height of this equation. So like always, let's go ahead and get started. And we always start with Bernoulli's equation. So let's go ahead and get started with writing that out. Of course, that is the difference between the two pressures. So P2 minus P1 divided by its density rho. And values of the two velocities, V2 squared minus V1 squared half plus the heights. Right, Z2 minus Z1 times G equal negative 4F V squared over D2D. I'm actually going to go ahead and take this 2 out and start off with a negative 2F. All right, nice and easy. All right, so let's go ahead and get started. Like we stated, this is an open channel and water is flowing through it respectively at both instances, 0.2 and 0.1, and therefore there is no change in pressures, so this value is negligible or it goes to 0. We can kind of forget about that. And then our velocities, the second term, we can also kind of forget about that as the two points 1 and 2 have the same cross-sectional areas, and therefore they will be flowing through at the same velocities. So this expression is also negligible. It goes to 0, and so we're just left with the values in terms of z, right? And if we can see is what we use this angle perspective for, and what we can do is utilize it in our favor, right? As you can see, z is of course a value of height, and this of course is a value over delta x. I forgot to put that in, but that is our value for delta x, right, or width. And what we want to do is get z in value of delta x, so we can go ahead and cross it out on both sides. So we all remember trigonometry. We know how angles work. So we know that the difference between these two, of course, is going to be negative, as 2 is lower than the first one. And of course, this is also can be written delta x in terms of sine, right? The difference between these two, delta z, right, can be written z2 minus z1. Delta z can be rewritten as negative delta x sine of theta, right? Nice and simple, so we can go ahead and plug that in and later cross out the common factors. So I'm actually going to write this back up. So for this term, we said we're going to have negative, and I'm pull the G out front. Same with the delta x. Sine of theta is equal to this right-hand side remains untouched, right? V squared over the diameter. Then, of course, you can see now we have the common terms. Of course, like I said, delta x, we can go ahead and get rid of that. And, of course, our negative as well. Right, we have a negative on both sides, so we can go ahead and rewrite this expression. I'm going to erase it all. So we're ended up with G sine of theta is equal to, we had 2 f v squared divided by m, right? Because we had delta x g sine of theta, they were both negative, we wrote that out. So with that said, we can go ahead and get rid of this old Bernoulli expression, as this is what we can refer to now. So if you may notice where we're going with this now is we're going to get an expression for g and kind of use the root function to optimize when it is its actual value, right? And so the next step here, as you may remember, is that we're going to compare this get the value for the, or compare this to a circular aqueduct, right? So to kind of simplify things, for the shear rate, what we're going to do is think about this in terms of a circular aqueduct. So we have water filled up to the brim, and it is flowing down through this aqueduct, and it is going straight down. We're going to, instead of calling this the height, I'm going to call this delta x, so that it will help us out in terms of bringing this equation back into this instance and kind of smushing those values out. So what we can do with this is work out a force balance equation so that we can get a value for the shear stress, right? So what we can do is that the force of this water, I should have done this blue, but that it's going down, is equal and opposite to the force that the shear straight or that the material opposes on it, right? So what we can do for that is simply write that the weight of the liquid, which in this case is also water, multiplied by the acceleration due to gravity. However, we don't know the mass, but we kind of do. We're going to have to rewrite that. How can we write that? Well, due to it being water, we know its density. So we can write it as rho multiplied by the area. So we're going to have delta x multiplied by this, which we're going to call it A. So A delta x, and then again multiplied by g still, right? And what is this going to be equal to? Well, I said the term shear rate or shear stress, right? And it's called tau. It's right here. And then, of course, it's also going to be multiplied by something called the wetted perimeter, which is the perimeter that is wet from this instance. So in this case is the circumference, right? And then, of course, multiplied by dx, which is the height, right? So we can rewrite this expression as rho a delta x g is equal to tau multiplied by wetted perimeter multiplied by delta x. As you can see, we can rewrite this a little bit easier. We can get rid of these delta x's, of course. Start off with that. And then we can get this in different terms for, I'm going to start off for just rho g by moving this a to the other side. So we're ended with rho g is equal to shear rate or shear stress multiplied by the wetted perimeter divided by area. And this is where things get kind of interesting. What we can do is write an expression or a ratio for the wetted perimeter to area. As you may recall, I said that the webbed perimeter is equal to circumference, and we know what the area is, right? We know that the webbed perimeter is circumference, so that is equal simply to pi d, right? And then the area is simply pi d squared over 4, right? Pi d squared over 4, right? So if you multiply that out, we have 2 pi d's. This goes away. This becomes a d. We get the 4 in the numerator, so we get 4 over d. 4 over the diameter, right? Yes. So then we can go ahead and rewrite this as rho g is equal to the shear stress multiplied by 4 over d. And then, of course, we can go ahead and rewrite this in terms of g so that we can later plug this into here. So that we get g is equal to 4 times tau divided by rho d, right? So now what I'm going to do with this, like I said, I'm going to plug this back into our leftover Bernoulli's equation and start machining it out. So if we go ahead and do that, I'm going to end up with 4 tau divided by rho d sine of theta is equal to 2f v squared over d. Now what I'm going to do is kind of free up some space so that we can keep working on this equation. So this we need these bottom two. So I'm going to write these equations back up top here. The 4 tau divided by sine of theta is equal to 2f v squared over d. Okay. Then of course we have g is equal to, there, I know that, we don't need to make that up. So we can erase this out. Alright. Sweet, you're right. So what we can do from here is work this expression now so that we can get an equation for tau, the shear stress, right? So if we multiply this out, we get this d, and there's a d in the denominator, so this goes away. So I'm going to start off with tau. We're still going to have fv squared, the numerator, right? And then also multiplied by rho, right? And then divide by 4, there's a 2, so this becomes 2, and then sine of theta. I think that's correct. Divided by 2, rho fe squared. Sine yes, okay, so this is now our expression for the shear stress, and we can apply this equation as well to our instance up here, not circular, expecting that it's going at the same velocity. So we can also go ahead and get rid of this as we're done with this situation and can start to apply it back to our square aqueduct, right? So for our square aqueduct, this is where we're at for our shear stress, and of course we still want to get value for G, right? Like I said, that is our main goal. Get the real expression for that. So the next step here is to go ahead and plug. As you can say, we still have some issues here. I shouldn't have erased that. Okay, because we had to plug this back into the expression. If you may recall, we had rho G is equal to multiplied by the wetted perimeter divided by area. Right? Sorry, before we go ahead and do that, we got to get our expression for G. So we go ahead and plug this back into here so that we get an expression for G in terms of this square aqueduct. So if we go ahead and plug that in, we get rho G is equal to rho FV squared divided by 2 sine of theta, and then multiplied by the wetted perimeter over the area. And what that looks like for this instance, the wetted perimeter simply be what is touching here. So we'll have the width, and then of course we're going to have the height, but on both sides. So we're going to have 2h plus w. So that's what we're going to have over here. 2h plus w is our wetted perimeter. And as for our area, of course, we're going to have the multiplication of the two, which is the width multiplied by the height, or HW, I'm going to call it. And then now we can go ahead and work this out so we get a value for G. And of course, you see there's both rows, so we can simply erase them out. So that is our expression for G. Right, and now we can go ahead and erase this off the board. We don't need that. And so we're almost there in the home stretch. However, you may notice there's some inconsistencies. There's some issues with our expression. We don't know what F or V are, right? We need to get expressions for both of those. So let's start off with V. For the velocity, we know that's pretty simple, as we are given Q, the volumetric flow rate. And we know that Q is simply equal to the velocity multiplied by the area, right? HW. So that we can get that the velocity is equal to Q divided by HW, right? So we can go ahead and plug that into our expression for V. All right, I'm going to go ahead and plug this here. So G is now equal to F, and then we're going to have V squared. So we said we're going to have Q squared in the numerator, right? And then still multiplied by 2H plus W. And then in the denominator, we're going to have 2, and then the Q, or the V squared, became divided by HW, and it's squared, so we have HW squared, and of course we still have this down here, so we're going to have HW cubed. So 2 multiplied by HW cubed multiplied by sine theta. Alright? Beautiful. Alright. I'm going to rewrite this a little bit easier to read. HW is cubed sine of theta. There we go. There is our expression for G that we will go ahead and plug into our Python code. However, of course, like I said, we are still missing value for F, right? And if you may recall to one of the earlier video series in one of my channels, in this channel, we worked out an expression for Churchill. If you remember who Churchill was, he came up with a lot of useful expressions that help us derive the values for F in this expression. We will be using previous code and plugging that back in for F. So we'll be using Churchill to give us an expression for F, and what that's going to look like. So remember Churchill. Equation that we worked out. What it needs is Reynolds number, right? And we all know what Reynolds number is. Reynolds is rho VD over mu. Right? It's necessary to know. It's simple math. We all know what Reynolds number is, and we know we're dealing with water in this instance. So we know rho, we know the density of water, we know mu, the viscosity, we know v, the velocity it's going at, since we know q, and then the only thing we don't know is d, the diameter. What we're going to do is relate it back to our circular aqueduct instance and get an expression for d. So if you may recall what we got for the value of the wetted perimeter to the area for the circular instance, we had 4 over d, correct? And then for the square aqueduct, we have this expression 2h plus w divided by hw. So nice and simple, all we have to do is cross multiply to get an expression for d. So if we multiply, we get d times 2h multiplied by 4h, so that we get d is equal to 4hw divided by 2h plus w. All right. So let me go ahead and circle this. Now we have our value for the diameter, or the correlation of diameter between the square aqueduct to the circular. So we get an expression for Reynolds number, so we can plug that in for F. We also know Q, the value for Q, theta, and everything. So, and then also, of course, we have our expression for the shear stress. So with that being said, we can now head into Collaboratory and plug these equations in so that we can get a value for our height. Hello, and welcome back to Collaboratory. Now that we've gone ahead and solved for these equations on our whiteboard, we can go ahead and plug them into our code so that we can get a value for our height. So I've gone ahead and, as always, imported numpy, as we'll be using many different math functions, and of course our root function. And if you have trouble remembering what this does, please refer back to some previous videos. I have many explanations of how this optimizes our values. Of course, some knowns for our situation. We're dealing with water. We know the density, viscosity is 1 to respectively, and also the acceleration due to gravity, g, right? That's what we're going to be optimizing. Then, of course, as I said earlier, I copy and pasted an equation from our previous video for our Churchill, which we plug in Reynolds number and the surface roughness to give us the fanning friction value. So with that being said, let's go ahead and hop into our problem. So as always, we want to give in our values. We know that the volumetric flow rate Q is equal to 1 meter squared cube. We also know that the width, right, is equal to half a meter. And then we know theta. We know theta is equal to 15 degrees. So what we do is 880 times 15 times MP divided by 180, right? Those are our 3 given values. So now we can go ahead and plug in our equations into a whole equation so that we can give it a value for g. So I'm going to define an equation. I'm just going to call it EQ. Of course, we're going to pass a vector inside of it, and this vector we're going to unpack it as our height. Right? Oops. And then we can go ahead and plug in our equations. So I have this pulled to the side. And go ahead and get started. So we know tau, so I'm just going to call it big T since we don't have that yet. And rho times f squared, right? V squared by the feigning friction factor F, and that is all divided by 2 times P of sine 2 times MP sine of theta. That is your value for tau. I'm actually going to call this tau so we don't forget later on, don't mess up with that. And of course it's saying we don't know what V or F are. So I'm going to sorry, I'm going to go ahead and plug that in. We need Reynolds number and a V. So actually I'm going to start off with V. Keep it lowercase, right? We said is Q divided by HW, right? Value for V. Now we need a value for the feigning friction F, right? So we need, of course, Reynolds number. So RE is equal to rho V times D divided by mu, right? We know rho, mu, and V, of course. Oh, doesn't know the width. We have capital W. Right, that should be good. Of course, it doesn't know D either, so we can go ahead and plug this equation in, right? Relating it, which is 4HW divided by 2 times H plus W, right? To make sure there's no issues with the multiplication, right? Alright, should be good. This is a small W. H, yes, should be good. So now, of course, we're missing F. Of course, F is due to the feigning friction. So CH, and we're going to put RE, the surface roughness, or the Reynolds number that we get. And for ED, which is our surface roughness, I'm just going to give a generic value of to the -6. Now we have all of our values for tau, right? And we can, of course, now plug that in for G, for our final expression, right? We want this to return this final expression. So, of course, we want F times Q squared, right? So, Q squared, and of course we have multiplied by 2 times H plus W. Let's space this out. It's Q squared multiplied by 2H plus W. That should look good. And that whole thing divided by 2 times, we have HW cubed. So HW cubed, then multiplied by MP sine of theta again, right? And that divided. Alright, so this should be good. And what we want to return is the value of of course, we said we want to optimize the root function, so we want to subtract this from the actual value of g, right? Figure out what value of h makes this equal to 0. So this should all be good. We can get rid of that, make sure this is alright. I think that looks good, so we can go ahead and utilize our root function, right? So call our root. Recall we want what equation we'll be using. Equation, right? And then what we will be using will be initial value of, let's just say 0.2, just for a guess. And that is all we need, right? Oops, the light just went off. Let me here. Okay, it doesn't matter. You guys can still see me? Yes. So press Shift Enter, we should get our value. No, there's an value or an issue. Maybe we don't even need tau, so we can actually get rid of this. Save that. Maybe try lower 0.1. No, still an issue. Oh, well, of course. Okay, well, I just messed up here. We don't need this here. Apologize for that there, but out here. Okay, so now we should be good. Shift Enter. Oops. Shift Enter this. There we go. We get some values. We can go ahead and do .xo2, just pull out what we want. There we have it. We get a value of 0.141 meters for our value of h, for our height of water in this aqueduct. So hopefully this video was of good use to you guys, and I'll see you guys in the next one. Thank you.